So quick thing about me, yeah, as Kyle said, I'm a security principal at MongoDB. This is my focus. My earlier slides had me on Kenn White, but you know, these times being what they are, I'm on Mastodon now. All right. Let's talk about some popular misconceptions around encryption. And I don't just mean by developers, by the way. I mean by people in the InfoSec sort of world or space. So if we think about things that are common in the vernacular of our work, we talk about data in transit, we talk about data at rest, and some of the technologies around that supports it. But I wanted to kind of dive in a little deeper because in the context of a database, and so the majority of the talk is going to be about the work that we've done with a special type of encrypted search and some new techniques. When people refer to database encryption, that's a loaded term. It can mean a whole lot of different things. Sometimes to regulators, it just means you're encrypting your disk. And so, if you've got like healthcare data from an analyst's laptop or something, and the laptop's stolen, the difference between volume encryption or not could be a $20 million fine or no report. It's very different when you think from sort of an operational defense perspective, or just from an institutional risk perspective, right? So in the context of a database, disks rarely rest, right? Once you mount a database and it's up and it's an operational workload, it's working hard. It's talking, it's got caches, it's got buffers, it's really active. So storage at rest provides an important control, right? And so things we think about are snapshots and backups and so forth. But if a database is up and running, it's not resting. And so storage at rest isn't helping you much from most kind of common, active attacks. So when we talk to users, a lot of times particularly veterans kind of in the, in the IT space, sometimes I get these confused looks like this is a solved problem, right? Because X or Y database has had transparent encryption for over a decade, and it's great because you just turn it on, and the developers don't have to change what they're doing, right? They just write their code and their queries, and things just work. That's right, absolutely, it's transparent. They don't even think about it. And the reason it's transparent is because the server's holding the keys. The server's holding clear text. Sometimes there's some, Cirque du Soleil level gymnastics in terms of how they get that key, but the point is that somewhere on the database, the sensitive or confidential information is in clear text, right? Sometimes people discuss in the context of secure hardware enclaves. Hardware enclaves are terrific, and they provide some really important controls. In the context of, say, a cloud server, a cloud database, it's less clear. Certainly, a lot of cloud providers have been sort of jumping on the Intel SGX, the AMD SEV, the equivalent in the Amazon Nitro world. And that has, has some nice benefits. It actually makes more sense from the application side, right? If you are dealing with keys or sensitive data. It's not so clear, though, what it's providing you when you run an entire database inside an enclave. And I didn't even know this existed actually until about a year ago. I assumed from kind of earlier exposure to this, these structured enclaves were really small, and just a few megs or a few hundred megs. That's not true anymore. These are now multi-gigabyte, memory spaces, active spaces. But there's a problem, because if it's running on the server and it's outsourced, there's going to be a question in terms of who has access to that, right? And so are some of these things sort of hand-wavy? Are they pinky promise as a service? Or are they really getting to kind of first principles, right? And I think part of this actually is a shared lexicon issue, right? When CIOs and developers and crypto people talk about encrypted search or encrypted databases, a lot of times they mean something completely different, right? When I say encrypted search for our purposes here, I'm talking about the way it's used by cryptographers, right? So this is end-to-end data that can be privately queried, right? Queries can be performed against a database server holding encrypted data, but that does not have keys, does not have access to the clear text, and that's the crucial distinction. So we have to, when we're developing security models and architectures, really think through that trust dilemma, because it is, right? We have to think, about authorized operators, right? Privileged server-side users, DBAs. Now, obviously, DBAs need to be able to, back up systems and to, run patches and things like that. But do DBAs, by virtue of their privilege, in, say, an HR database, do they need to see people's individual social security numbers or their payroll routing numbers or things like this? A lot of times the answer is no. And so the problem is a lot of systems don't give you an option. It's either, sort of God level access or not. Same with sysadmins, right, on the Linux or Windows side. And how about the custodian's backups, right? Now that's a case where, encryption at rest actually makes a lot of sense, right? If you've got snapshots in the cloud space for storage or things like that, that may make sense. So, sort of related to this, one of the things I want to sort of raise is, what are the true security guarantees of end-to-end encryption? So I think a lot of people in this room think that you've got a good mental model for it, but I really want to push hard on that, because I think most of us do, in the sense of like secure messaging apps like Signal and WhatsApp and so forth. But sometimes not, right? End-to-end encryption doesn't help if the device has been compromised. End-to-end doesn't help if the application's been compromised, because the application is the end in the context of a database, right? So what's a threat model? How do we think about actual guarantees? Where do the data flow? Who holds the keys? These are fundamental questions. And I remind you, we should probably post this at least in one deck in every Enigma presentation, because there are critical distinctions between levels of trust and service providers and people with different privileges. And I really want to kind of underscore that point. But again, in the context of a database, what can an attacker discover? What information does a database leak? What information, are the leaks exploitable, right? Because there are some models in the academic world where there's really virtually no leakage at all. The problem is your keys are now gigabyte sized, and it takes sometimes minutes or hours to run a query. And that's maybe not practical in an operational workload. More importantly, can we describe, in all these different sort of techniques that people have tried over the years, can we describe leakage formally? And it looks like we can. There's some really interesting initiatives originally started out of the Brown University's Encrypted Systems Lab, looking specifically at this, looking at how we can define and approach as a field the sort of an empirical way of formally defining leakage. All right, so just a few preliminaries before we get started. Borrowing from Thomas Batasek, you probably shouldn't freelance cryptography, right? Which is to say, if you don't have domain expertise, careful what you're walking into, because it could kill you. All right. Security models should be as rigorous as possible. Security definitions should be as precise as possible. This slide I love for so many different reasons, because I've looked at a lot of security models where there is sort of an implicit step about, and then a miracle happens. Do it yourself and fail fast makes a lot of sense in a lot of contexts. Probably doesn't make so much sense in crypto context. Developer usability, right? When I first started looking at this sort of carefully about 5 years ago, there's like hundreds of different options on different GitHub repos and sort of academic like proof of concepts and these sorts of things. But a lot of them assume that you can do things like, well, let's develop a brand new database from scratch, right? Let's figure out all the hard problems of, say, replication and sharding and scaling and and some other things that I'll get to in just a minute, and not really taking into account what I like to sort of refer to as a mediocre Python developer, right? I've been given in my day job a responsibility of, you've got certain data, it's sensitive, figure out a way to make it protected, figure out a way to keep that confidential. And then of course, there's lots of thoughts on the orange side. So some things about distributed cloud databases, right? And we don't necessarily talk about them a lot. And if you're not sort of in the trenches, you may not see this as much, but it's worth sort of underscoring, right? Things break. They break a lot. Networks get flaky. The connection between a web app or a web service and a database or a database service can sometimes be unreliable. Replication's really hard because it's one thing to have a developer laptop and one small database running a few thousand or 100,000 records. It's another when, as is the case for some of our users, you're putting tens of billions of dollars of transactions through a system, right? There are certain classes of data and system protections that are just in a different, on just a different plane of existence, right? We have some customers that are running entire national pension systems. So by that I mean every infant, mom, dad, working adult, pensioner in the country, in the entire country, their data are stored in these databases. And this is financial information, this is social services, this is pension data. These things really matter, right? Partitions are a problem. Sometimes things just die, and worse for developers is the sort of difficult to reproduce bug, right? Why do things sometimes kind of only semi-die? So let's take a step back for a second. Let me be the one to ask a really basic, stupid question. Why do we use a database, right? What are some of the useful things a database does? Searching. Seems kind of obvious, but it's important to say, because a lot of the encrypted search literature is looking at a, say, PDF or Word file that's been encrypted, and it's just like, thousands of these static documents, and there's a keyword search or something. And that's useful, and there's tons of use cases for that, but it has nothing to do with an operational, database. And about concurrency, because if you're one user talking to one standalone small instance, that's fine. But what happens when you have thousands and thousands of concurrent users? What happens when you have not just one client application talking to a database, but hundreds of thousands of concurrent mobile apps, right? Tons of legacy integration, things like middleware, things like these huge HR or fulfillment systems. The academic literature doesn't speak much to that at all. So what are the kinds of searches we're talking about? Well, this is a basic one. Let's say I want a date of birth on encrypted data, and I've got a birth date. This is, there are a lot of techniques to do this, but this sort of exists in different places in the world. But how about if I want to search expressively? What if I want to search for like everyone that's, say, over 25, or anyone whose last name, I'm a customer service person, and someone's got a long last name, and I want to just type the first few letters of the last name and have it sort of fill in. How about if I want records in a healthcare context of a certain social security number that ends in a certain number? Credit cards, that's another great one that we see all the time. Customer service agents may not need to have access to the entire record, right? How about full text search? How about if I could search all these, hundreds of millions of records to find things that had certain keywords? That would be really useful. That doesn't really exist in a practical sense in any database right now. What types of data are we talking about, right? So this is the data that users care about. Strings, dates, numbers. Banks really care about decimal data types. They really care about precise financial values, objects, and documents like JSON. So from my view, as somebody that works with so many different kinds of use cases and institutional customers to startups, just to sort of frame the conversation, give you a sense of where I'm coming from with Mongo. So we run a globally managed distributed database service, about 2.5 million active clusters around the world, and a cluster means a primary server and replica sets that read that data, and if the primary server dies, the replica sets sort of take over. We're operating in 200 data centers around the world, 8 different cloud providers, everything from like tiny little developer sandbox instances of like Hello World to petabyte scale, where literally the same database has nodes running in GCP, Azure, Amazon, and maybe on-prem. Really complicated, multi-hundred sharded clusters. We generate about 100 million cluster node certificates to date. Actually, sorry, I take that back. That's about annually we're doing that now. So really massive volume. One sort of thing I should say, what's MongoDB? It's an open source NoSQL database. Probably not the kinds of documents that I think a lot of people, sort of comes to mind. These are native JSON documents, and including complex subdocuments. It's distributed architecture by design, geolocations around the world, really vibrant developer community, over 250 million downloads to date, lots of students, lots of developers. Native JSON documents, you're thinking to yourself, including complex subdocuments. What is a JSON document? That's a JSON document. This is fake data, obviously, although I think that's the actual phone number for the equivalent of the White House in Germany, and the card number is right off Stripe as one of their test card numbers, and I forget how it's pronounced in German, but the equivalent of the Social Security number is, that's what's printed on model application, so no confidential data leaking here. So mostly I want to talk about sort of a journey, or sort of share a story with you, right? Thinking about research models of databases, thinking about prototypes, some of the things that we've gone through to sort of get to an interesting implementation. Some of the trade-offs we've made, real-world performance, et cetera. And crucially here for this audience, things that we got wrong and some lessons that we learned. Lots of different approaches in the academic literature around encrypted search, tokenization, property preserving encryption, et cetera. But are these actually suitable to a generalized purpose database? That's a key question. I really encourage you, if you don't know this history, I've got a couple of links in the next slide, to read up on Yaqub al-Kendi and sort of the golden era of Arab cryptanalysis. On the left is an original manuscript, on the right is sort of a translation of one of his cryptanalytic treatises that he did. But he's sort of considered one of the, top, like pioneer sort of fathers of cryptanalysis, and he was a brilliant person. The point of that is that one of his early works on letter frequencies still works today on a lot of encrypted systems. So I've got some links there below, and I'm happy to add some more in the slides that we share online. But anyway, fantastic story. So let's jump ahead about 1,100 years or so. Working with a lot of different users, a lot of different customers, a lot of different complex use cases, I got this question. Right? How can we be safer? How can we keep data more confidential? We're not looking for a silver bullet. We're not looking for some panacea. We want ways to be able to, keep our data more safe, but still be able to use it. So I took a leap of faith and reached out on that site, which shall not be named, to Seni Kamara. And this is what I sent. This was April of 2018. A year later, we launched sort of our first generation of field-level encryption. It's an end-to-end type, and about 6 months after that, it was in general availability. The next spring, and we had a great collaboration. He and his team in the Encrypted Systems Lab at Brown University. It was a terrific collaboration. He came and visited, and we had a conversation over coffee, and that sort of changed my perspective on so many things that are possible. Partly because the description, the way that a lot of the academic literature was characterized, and some of their own work was, we have this really cool way to do expressive searches, rich searches on completely encrypted data. But step one, you have one laptop and one database. Step two, you have a cache that runs on the application side. So developers need to figure out how to run a distributed cache and kind of keep that to themselves and manage that and distribute it and make sure it doesn't fail over and things. And then you need to kind of modify a lot of how the system works. What he shared with me was a breakthrough that their lab had done where you don't have to do that. You can actually emulate that state in a database in a blinded way. They hadn't published yet. It was sort of, kind of breaking, and it was just mind-blowing to me that was even possible, right? And so that began a long journey around this thing that we now call queryable encryption. So what are some of the design requirements? Queries that are actually useful, right? Legacy friendly, and by legacy I mean things that shipped last year or that are still in development, right? I don't mean legacy, mainframes. Multiple clients concurrently, stateless. It has to handle the flakiness that we talked about before. And developers have a hard enough problem with basic system security without having to deal with client-side caches and distributed things like that. Crucially, it needs to be efficient. It has to be sublinear. The difference between 1,000 documents, 1 million, 25, 100 million documents, it should be sublinear. A lot of the academic work had been done in a way that's superlinear. So works great on 10 records, 100, 1,000, 5,000. Beyond that, it's painful. And so you can throw cores at it, right? You can throw more CPUs, but it's kind of like racing the Indy 500 with llamas. You're not, there's only so much you can do. High-level flow, let's say you're a Python developer, you have a query on an authenticated client, DB billing, fine, I need that social security number. The basic way that we ended up is that the driver that runs on the application side picks that up, talks to a key provider if it's not already been cached, and what it sends to the database is a type of encrypted search tokens. They're not a one-to-one relationship with the actual data, and the individual data that are stored in each of the records are encrypted with randomized encryption, which is to say, for this person's social security number, if I've got 3 entries in the database, each of those social security numbers is stored differently. It's the strongest form of modern authenticated encryption that's possible. How does it work? Okay, here's the boring part. Basically, pretty standard sort of contemporary authenticated encryption. Here's some of the details. There's some derivative keys that are used, but these are basic building blocks that the NIST approves, the PCI people approve, that are crucially more important, are available in nearly every operating system and every language framework. Key management, tons of opinions and thoughts on key management people have, but all that to say, we made it as agnostic as we can, right? So we use envelope encryption to protect field keys. If you trust AES to protect your data, you should trust to protect your keys as well. The database can't ever access raw key material. And again, any of the top 3 cloud providers, if you want to use hardware modules, that's fine, HashiCorp, et cetera. These things are crucial, particularly in regulated environments. But here's the key thing. Here's the innovation. The innovation is a new type of functional search index. So let's take that JSON document before. We encrypt that with normal, sort of standard AES, and that's safe. In addition to that, we now build encrypted indexes. These are using a technique called structured encryption. Client stateless, the database maintains blinded state. Again, distributed, scheme robust to failures, high contingent, et cetera. We use a technique called encrypted multi-maps, just a fancy way of saying an encrypted dictionary or an inverted index. Here's more of the details there. There's a formal security definition that's in the works, we'll be publishing in the next few months ahead, called OST1. That's the particulars, but it talks about gets and puts and things in that context, and crucially, sublinear response time. About those JSON documents. So what does this look like? What does it actually look like to a developer? This is a DBA view. In this case, I've got global cluster admin privilege, which is to say I'm God in the database. And this is all I can see. Those fields with stars are individually encrypted, right? This is what you see if you've got access to the end-to-end keys. And the DBA, again, won't see that unless they've also been given the end-to-end keys, which kind of defeats the purpose. So some trade-offs, preliminary metrics, give you a sense of it. Maybe 2 to 4x additional storage costs. There's some additional details about the structures and things that we add in place. The actual documents themselves, there's just a minimal amount of additional storage. Finds, queries, very fast. So on 10, 20, 25 million document data sets, these are in the order of milliseconds. writes are a little more complicated. We're still sort of working through those, looking at parallelization, looking at some other techniques. If you're sort of a 90-10 sort of web app or a web service where the vast majority of what you're doing is reading and occasionally you do inserts or updates, it may be a good fit. If you're doing 100 million documents constantly, every hour in a batch process, it may not make sense. But again, we're working on some parallelization efforts there. Take all that with a grain of salt because we are very much a work in progress. This software is in public preview. The goal of that is beta level stability and behavior. It is not for production use. We literally have a red box at the top of all our docs pages that say, don't use this, we'll have breaking changes, date format changes, or data format changes will be frequent, et cetera. The key thing is looking at user experience, taking user studies, talking to Python developers, Go developers, C#, Java developers, step by step from hello world to real architectures. And everywhere possible, we're trying to think, how can we reduce or eliminate choices, right? How can we make it less confusing or less sort of possible to kind of shoot yourself in the foot? Oh, and again, more towards opinionated and safer defaults. The technology is Apache license, it's open source, it's on GitHub. All the commits are public. Compass is sort of a graphical viewer. The shell is a sort of command line interface. The driver support is beta, experimental. I really want to kind of underscore that. Our releases that you can download are probably 4, 5, 6 months sometimes behind Nightly branches because we're moving so quickly. These are some of the different packages, and yes, we do ship for IBM Z series if that's your thing. Wanted to give some special thanks to our crypto team. Over the last year and a half, we actually now have a 5-person PhD cryptography team in-house. These are some really talented people that have deep subject matter expertise. I don't know if you've seen that meme where the guy's like, there are dozens of us. Well, this is a very niche, kind of community. So we are very happy to have this kind of collaboration in-house. We've made some changes to the core database, but not nearly as many as we have on the application side. Okay? This is just a snapshot of some of the folks that are involved. Probably twice as many now at this point across all of our different teams. I want to leave you with a couple things and sort of wrap it up. So, current landscape on encrypted search, this is a really fast-moving area of academic study. These are really interesting, rich, expressive techniques that are kind of being developed, as are the attacks, as are leakage analysis, as are sort of, better defining these security models. Some really promising developments. I don't want to give short shrift to things like homomorphic or multi-party computation, differential privacy. Those all have key uses, but in terms of a general general purpose database, it's likely that we're going to land on structured encryption as sort of the technique going forward. Happy to talk to more folks afterwards, but again, we're never going to claim any kind of silver bullet or magic solution. Just making it more difficult, raising the bar on attackers. That's the goal, and learning as we go through all this. So I'll leave it there. The future of practical encrypted search is bright. Thank you.